Okay, so in this video we're going to do an exponential decay problem. Our model for this is going to be a of t equals a0 e to the negative kt. I use a because it's normally, a lot of times, very frequently, you can do an exponential decay problem with half-life, which is the example that we have here. That's not saying that's all of them. You could certainly have a population model like this if you had, let's say, the zombie apocalypse. So you could also do depreciation of a house or a car with this model, and it would work out just the same. All right, so they say that the half-life of cesium-137 is 30 years. I actually looked that up. And we want to know how many years would it take for only 5% of a sample to be remaining. Okay, so in this problem, notice a couple things. They told us a half-life, so that's going to help us figure something out. They want to know about how long it's going to take for 5%. They did not tell us the decay rate, and that's a very important thing. So let me write down the model. Okay, so that's our model we're going to use. We don't know how much the original sample was in terms of what's the mass. But that's no big deal because we know how long it takes for half of it to go away. So if you're uncomfortable doing what I'm getting ready to do, you can let A0 be 100. Half of 100 would be 50, right? So that you could do something like that if you really wanted to. But I'm going to say a half A0 equals A0 e to the minus k, and we know the half-life is 30 years, so I will say 30. Okay, so notice what happens. This is why we don't need to know the original amount. So when we divide by A0 on both sides, it cancels off. So we're going to have a half equals e to the minus 30k. We take a log, and then we'll divide by that number. So natural log of a half over negative 30 is k. And if you look in a textbook, so a lot of times a textbook, they'll say the decay rate is the natural log of 2 over the half-life, something like that. I would say don't memorize that because you don't need to. This is the same thing because natural log of 1/2, if you remember the properties of natural log, would be natural log of 1 minus natural log of 2. Natural log of 1 is 0, so negative natural log of 2 over negative 30 gives you the same formula. Okay, so I did this on my fancy schmancy calculator and I got 0.023. So that means A of t equals A0 e to the negative 0.023 t. All right. Now we can answer the question. So we want to know how long it takes for 5% to remain. So 0.05 A0 equals A0 e to the minus 0.023 t. And we can do the same trick. We divide by A0, take natural log, divide by that number, and so I'm going to go straight to the chase. So natural log of 0.05 divided by negative 0.023, that's roughly what t is. And I did on my calculator, and I got 130.249-ish years. Let me just say one thing about this stuff. When you're doing a half-life problem frequently with carbon-14, the half-life of carbon-14 is 5,700 and some years. If you're doing that, you need to use more decimal places because it's going to be the decay rate is going to be a really, really small number. Textbooks love problems like this because the half-life is a reasonable time. 30 years is reasonable. The half-life of some of the more recent radioactive elements that we've discovered that are only around in a radioactive state is like almost nanoseconds. So it's kind of unreasonable to use, or a half-life of uranium-235, another example. The half-life of that's about 700 million years. So it would be unreasonable to do a problem in a textbook that would have something like that because the decay rates would be just ridiculous. All right, I'll stop here.